Hey guys, I'm finally getting back to the GE800 television. I'm almost done with the recap. I've got a few more electrolytics to replace, namely this multi-section cap right here. Things are a little bit cramped underneath, so I'm having a little bit creative. But before I bother getting the B+ power supply hooked up, I want to try to get all the tube filaments to light up. And that involves something that's inside here. But before I get into that, a little bit of background on this TV. Unless I'm mistaken, this is the very first series strong transformerless magnetically deflected television. Yes, there were series strong transformerless electrostatically deflected TVs, but I think this is the first magnetically deflected. And that required a little bit of innovation, namely a 19 BG6 horizontal output tube and a 25 W4 or 25 Z6 damper tube. Why? Well, generally speaking, when you've got a series strong set, you want all the tube filament currents to be the same, because they're all wiring in series, and all the current has to flow through all the tubes. Yeah, there are some tricks you can play by putting a resistor in parallel with one of the tubes that uses a little bit different current, but ideally they're all the same. Well, a TV, especially like the horizontal output tube, traditionally they would use something like a 6BG6. That wouldn't work with the other tubes like in the IF and the tuner, so they needed to come up with this. In other words, your typical horizontal output tube draws more than 300 milliamps, and that is what all these other tubes are running at. The other thing they had to contend with is, again, ideally, if you string all the tubes together and add up all their tube voltages, you get about 117 volts. If you've got over that, you've got a problem. If you have less than that, you can throw in a resistor to make up the difference. In this case, if you add up all these tubes and the tuner and the IF and the sound, you got way more than 117. So they broke it up into two strings, but if they did that, they didn't have enough voltage. So here's what they ended up with. Two strings, 300 milliamps each, and they tie together and go through this. Turns out the standard picture tube of the era uses 600 milliamps. So 300 milliamps, 300 milliamps, sum it together, 600 milliamps, and go back to the AC line. Well, if you add up all these strings, even with the addition of the 25 volt 25W6 and the 19 volt 19BG6 and the 25 volt L6 25 L6 audio output tube and so on, they just couldn't get all the numbers that up to 117. So they threw in these guys, which are 75 ohm glow bar resistors. Now, I'm not entirely sure that these two strings are equal value. We're going to do some math, because sometimes they would round things off, fudge things a little bit back then. Because they kind of had to use an off-the-shelf resistor here. There are only so many standard values out there for these glow bar type resistors. I did this once before, and I don't recall these being exactly the same, but we'll find out. But at any rate, if you add these all up, you don't get 117, so they put in series dropper resistors. I call them glow bar. Well, here's another issue you have to contend with. When tubes are cold, their filaments have less resistance than when they're at their operating temperature. Typically, when metal gets hot, it has a higher resistance. So what happens is when you turn on a series strong set, there's a current surge, which could potentially pop a tube filament. You don't want to do that, especially if it's a very expensive picture tube. So, glow bar resistors. That was an early term for thermistor, a thermally dependent resistor. That's what these are, hiding inside the high voltage cage. When they're at operating temperature, there's about 75 ohms. When they're less than that, they're higher resistance. They put them inside this cage because, well, it was a good place to keep them out of harm's way, and it's got a ventilated top so the heat could escape. The thermistor technology was a little bit primitive back then, so I don't really trust these even if they measure okay, so I do intend to replace them. Now, how much power do they dissipate? Well, let's do a little math, shall we? I know the filament strings are 300 milliamps. So, and power is current squared times resistance. So if we do 0.3 amps times 0.3 amps, and then multiply it by the 75 ohms, we get 6 3/4 watts. About 7 watts, let's say. And if, well, a good rule of thumb for power resistors is you want to use double the wattage. So let's assume these are good for 15 watts. So if I'm going to replace them, I could put in two 15-watt 75 ohm resistors. However, there's a few other things that we can take into account. One, we want that thermistor action. We want the resistance to be higher than 75 when it's cold. I don't think they make something that's quite equivalent to this these days. They certainly make thermistors, but more typically they are only a few ohms when they reach operating temperature, like the CL90 you guys have probably heard about being used in like an All-American 5 type radio. These are 120 ohms cold, but only about 3 to 5 ohms when hot, so we can't use that by itself. What we could do is take, say, a 68 ohm resistor or a 72 ohm resistor, those are kind of standard values, and put this in series with it, and then do two of those. That would certainly work, and that could be retrofitted right into here. We're done. But we've got a few other options these days. Depending on how much voltage you need to drop, you could also use a diode. I talked about this a lot in my Motorola VT71 restorations, because those will have a very similar situation where they have two filament strings and need to drop it. So one other option I've talked about in the past is to use a rectifier. These two filaments are going to the AC line. It's a sine wave. If you use a rectifier, it clips it. Now you might be thinking, well, it'll cut the power in half, or cut the voltage in half. Not quite. The math is more complicated than that. Luckily, there are online calculators where you can put in your line voltage, your tube filament string voltage, and it'll tell you how to, or what your options are. Now, you wouldn't just use a diode by itself, because then you still wouldn't have that surge limiting. So you put a thermistor in series with the diode, and possibly, if that's not quite enough, you maybe add another series power resistor with it as well. The diode will cut the power down without dissipating any power. That is the advantage to using it. They're very small. Use a 1 amp silicon diode. It's about that yay big. And then there's a third option, which I like the best if you can make it happen, which is to use a capacitor. A capacitor in series with AC and a load will introduce a phase shift between the voltage and the current, which will effectively reduce the power going to the load. If you get lucky and your numbers add up right, you can use a standard off-the-shelf value. Typically 8.2 microfarad or 10 microfarad is what I've used on previous projects. But you've got to make sure you've got the right kind of capacitor. Just any old standard film cap is not going to do the job. The kinds of caps we typically use on our radio and TV restorations, like the yellow axial lead caps that are rated for 630 volts, that's DC. You need caps that are rated for AC. Now, it's not going to be the full line voltage, but for safety's sake, you should get one that's rated for, I'd say, at least 100 volts AC. But that's not the whole picture. This is rated for 100 plus volts AC, I do believe. But if you look at the spec sheets, they don't really tell you the current, the AC current that's going to be going through this. Ideally, you'd use something that's meant for long-term, steady-state AC current operation, which would be a motor run capacitor is a common one, or some lighting systems use them. But those are big. You've probably seen these on refrigeration units, a big metal can with two lugs coming out of it, maybe PCBs inside. Luckily nowadays they make some out of polypropylene that are smaller, but they're still pretty big. I just happen to have one here. So something like that guy. But overkill, because it's 8 microfarad, which may very well be the right value for this, but it's rated for 420 volts AC. We don't need anywhere near that much. But they don't really make these smaller. I think I did find some that were used in like overhead fans, ceiling fans, I think is one source. So hunt around online, but all that is assuming that when we do the math, the capacitance value we come up with is something that we can get. If it's a really big number or kind of an oddball number, we may have to put caps in series or parallel, in which case where it gets too cumbersome and why even bother. So we'll see. We're going to run the numbers and we're going to explore the possibilities. Passive resistor, a diode, and a capacitor, and I will decide based on what numbers come up with which way I'm going to go. And once we got that, I'll put them in here, I'll leave the B plus disconnected, turn this thing on, and see that all the tubes light up. It may seem like I'm going into too much depth or dwelling on this topic too long, but I have my reasons. One is that along with the Bakelite cabinet, this is one of the distinctive features of this set. It has a rather different power supply design than other sets of the era. Also, you can apply these concepts to other sets. For example, the first Predicta Holiday I restored, I replaced that set's filament dropper with a motor run capacitor. And there are plenty of radios that also use filament droppers. And it's also, I think, a sometimes misunderstood concept, especially when you get into using capacitors or diodes to drop it. So let's start with the most basic part, which is what voltage do these add up to? I've seen manufacturers fudge the numbers a little bit because they had to use components they could obtain. So maybe these glow bars only came in 50 ohm, 75, 100 ohm. But maybe that's not the ideal value, so let's add these all up. Now something to keep in mind, this is not necessarily 25, 12, and 6 volts across these tubes. Tubes that start with a 12 are actually 12.6 volts. Tubes that start with a 6 are actually 6.3. However, a 25L6 is actually 25. And I think a 19BG6 might be 19.6. We're going to double check all of these. So roughly it'll be 25 plus 12.6 plus 6.3, 6.3, 6.3, 6.3. Then we get to this. What the heck is going on there? Well, these 12A series tubes, the 12AU7, 12AT7, 12AX7, can be wired for either 12 or 6 volt operation. They have a tapped filament. If you tie 4 and 5 together, you can run it on 6.3 volts. That's what they've done here. So it's actually 6.3, 6.3, 6.3, 6.3. So let's add all that up and then compare it to what this is and see what we get. And don't forget to add the 6.3 for the CRT down here. I went through and added up all the tubes, and here's what I came up with. It turns out the 19BG6 is actually 18.9. Because the standard 6BG6 is 6.3 volts at 0.9 amps. So to get the same wattage at 0.3 amps, multiply the filament by 3, so 6.3 times 3 is 18.9. So there we go. So let's see what all that adds up to. Get out my calculator app again. $25 plus 12.6 plus 9 times 6.3, we get 94 3/10. Let's do the other one. Plus 25 plus 12.6 plus 12.6 plus 18.9. That equals 94.3. They did do a good job. Alright, now they chose 75 ohms for the filament dropper. So if we've got 75 ohms at 3/10 of an amp, how much voltage is that dropping? Well, 75 times 0.3, equals 22.5. So what do you suppose 94.3 plus 22.5 equals? $116.8. They came pretty darn close to 117, didn't they? So here's another aspect to this little issue is line voltage today. In my area, it's more typically going to be about 123. So if we're going to redesign this dropper, it also gives us a chance to accommodate for a few extra volts. Or if you want your tubes to run a little on the lean side, design it for, say, 130 volts. There's some debate about prolonging tube life by running at a lower tube current. You starve them too much, you're compromising their performance and potentially damaging the tube, and your set is going to also may not be running properly. So you want to keep it within about plus minus 5 or 10% on the current going through your tubes, in my opinion. But better to be a little on the lean side than on the excessive side, that's for sure. So we're going to design ours for, let's say, around 127 to 130. That gives us a little bit of fudge factor if we're going to use a capacitor dropper. Now I'm going to dig up that spreadsheet. We've got some numbers to work with. Let's see, from a practical point of view, what can we actually implement? Here's the spreadsheet. I plugged the numbers into it. I'm going with the original specs of 117. We have 60 hertz here in the US. We've got about 94 volts across the tubes. They run on 0.3 amps. And this value I'll talk about in a moment. So let's see, if we just use a pure resistive dropper, we get right about 75 ohms and about 7 watts, as we discussed earlier. Dropper resistor with diode, we got negative values. It's just not going to work. It will drop too much voltage. And a dropper capacitor, we could, kind of an oddball value of 12.86 microfarad. And in this design, they recommend you throw a resistor in series with that cap to limit the surge a little bit. Now the capacitors will somewhat limit surge inherently. So when you turn it on and the load is low, when the filaments are cold, the capacitor phase shift will be even more, and it will limit the current going through it. But it doesn't hurt to throw a little resistor in series with it as well. And if we play around with this value a little bit, we can get that closer to a standard value, I think. Like 16 microfarad, you could probably find one of those off the shelf. We want to make this for a higher line voltage, so let's plug in, say, 130. Alright, now this dropper resistor has jumped up to 120. which again is a standard value, but the wattage has gone up considerably, but you could work with that. We still have negative values here. That's not going to happen. And now we're almost at 10 microfarad, which again is a pretty common value. This surge limiter drop, what number you should actually have in there, that's a little subjective. Basically, I would just tweak this so that you can, plus your capacitor is going to be like plus minus 10% anyways, so I would say you go with something like this. 10 microfarad, 33 ohm, maybe a 3 or up to, maybe a 5 watt resistor in series, or a thermistor like a CL90. You can definitely go with these values. Now what can we do to make this work so we don't have negative values? Well, it turns out that it's because its heater voltage is so high, I would need to drop that to say 90. Now we can do it. What would the effect be? So let's say we put in a dropper resistor and threw in, say, a 5 ohm resistor in series with it. We would have around 90 volts across the tube filaments, and it'd be less than 0.3 amps. The tubes would be running lean. So you could do it. You could do it. Say it was 90 volts across those tubes, the current would just be slightly less than 0.3 amps. So I think that is a real possibility. So I would suggest, if you're going to do this, either find yourself a 10 microfarad AC motor run capacitor, the type you use in a ceiling fan. I'll try to dig one up on an online selling site and show you what I'm talking about. Or a dropper resistor with a thermistor. And again, I'm going to show you one that you could use. I keep saying CL90 because that's a really common one. However, I would not recommend that. Why? A CL90 is designed for about 1 amp steady state current to reach its design target. With only 0.3 amps going through it, it's not going to get that hot. These things are meant to get hot. When they get hot, the resistance drops. With less current running through it, it's not going to get that hot. It's going to be higher resistance. It may be 10, 12 ohms, which is going to starve the tube to even more current. So I would suggest you find a thermistor rated for 1/3 of an amp ideally, or maybe 1/2 an amp, but not a 1 amp thermistor. I took those numbers I came up with from doing the spreadsheet calculation and started drawing up some schematics. I made 3 versions with the resistor, dropper, diode, and capacitor. And in all cases, the unknown, unlabeled component here, that would be the thermistor, which I have yet to determine what I'm going to use there. So for the resistive one, 120 ohms at 20 watts. Yes, big old honking resistors. They're going to get pretty toasty. Or, if we can make it work, we can just go with silicon rectifier. 1N4007, rated for 1 amp at 1000 volts, and 5408, 3 amps at 1000 volts, both overkill, but they're very inexpensive. It doesn't hurt to go over spec. You want to use something right in here. You don't want these to ever burn out. If you want to be really paranoid, you could throw a second diode in series. One fails shorted, you've got another one ready to go. The only thing to keep in mind is you will lose about 0.7 volts across each one of these. So as you add these up, you're going to be reducing the voltage going to the tubes. And then finally the AC version. 10 microfarad AC motor run cap. And I forgot to mention, you should put a bleeder resistor across the cap, so when you turn the set off, it will bleed off any charge that may have built up. 100K, 220K, something like that. 1 watt resistor. I think will do the job there. Alright, so these unknown components here, the thermistor, what is commercially available? What can we use? Well, I went through my stock, and this is what I have on hand. This is essentially a CL90, which many guys have used in many projects. It's been around for quite a while. This is rated for 2 amps continuous steady state current, and at that current you end up with about 2.3 ohms, which reached operating temperature. This is the same thing, made by a different company, somewhat different nomenclature on it. So rather than a CL90, this is an SL1212102, but the specs are the same. And then I have one of these guys. Same company, Amitherm made these, which is an SL1222101. So let's look at the spec sheets for each of these. So here's the SL1212102, which is essentially a CL90. So we got some dimensions, and then here's what we really care about. So at room temperature, it's going to be about 120 ohms plus or minus 20%. So when the set is cold and we turn it on, it's going to be adding about 120 ohms to the series string, which will reduce the current going into the tubes. As the temperature rises, the resistance will drop. Once you hit about 65 degrees Celsius, which you will get with about 2 amps of current running through this, you will be at 2.34 ohms. Now, our filament string is only 0.3 amps, so we're not going to get anywhere near up here. And I do give the specs for 50% max current, which would be 1 amp. That'll be about 5 ohms. Now, they don't have it on this data sheet, but I have seen the formula elsewhere that approximates it for even lower current. And I can tell you it will be considerably more than 5 ohms with only 0.3 amps of running through this. So it's really going to reduce the current going through the tubes. So this really isn't going to work out too well. I poked around on Mouser to see what else is commercially available, and it turns out that you don't get much to choose from when you get down to this range. Typically these are used with much higher current. You can see you get into the higher currents and you've got all sorts of options. But at the bottom end, 1/4 amp, 1 amp. So we can't use 1/4 amp, that's too low really, so let's see what we can get at 1 amp. And these are the cold resistances. We want something more than 5 ohms. That's not going to do us much good. So we've got 220, 120, and 60. I have some of the data sheets up here bookmarked. So here is the one that, well, it says 50 ohms here. It said 60 ohms on the other screen. So this is one that's 1 amp, and if you get up to 1 amp, you're down to 1.1 ohms. That's pretty darn low. We won't be quite there, but at 1/2 amp, we're 2.8. So at 0.3 amps, it'll be probably under 5 ohms or thereabouts. That would potentially work. Unfortunately, I don't have any of these on hand. What I do have, though, is one of these guys. 220 ohms cold. That's the highest I've ever seen commercially available. So it's really going to restrict the current on power up. However, the steady state current's a bit higher. So at 1 amp would be at 4.2, 1/2 amp 8.4, 0.3 amps going to be over 10 ohms. Now the diode is already, the resistor and diode combo is already kind of restricting current a little bit more than I'd like. So if I use this, I think we're going to have an issue. And something occurred to me. So in my design here, I'm assuming that we got AC coming in here, and then we need 2 branches for each of the filament strings. It's not quite true. There's no reason why we can't combine this and use one thermistor in here, and we'll have twice as much current going through it. In other words, 0.6 amps. So I propose we go with something like this. And since I've got one on hand, I'm going to try using this. So we should be somewhere between 4 and 8 ohms when we reach operating temperature. And we're going to be helped out a little bit because this can be located inside of the high voltage cage near the 19BG6 output tube, which is going to get quite warm, and there's also a damper tube in there. So we'll not only have its internal self-heating temperature from the current running through it, but the ambient temperature is going to be elevated. So I think we can get maybe down closer to that 4 ohm level. So I'm going to do a little experiment and see how this works out. And next time I place an order with Mauser or whoever else may carry these, I'm going to get myself some of these. Now, that's, again, the downside is the cold resistance of this is 50 ohms. The other's 220. And let's see, let's go back and look at this full selection. Let's check out the 120 ohm at 1 amp. I think I'll pick up some of those too. In other words, these guys. And 120, apply filter. Okay, we've got 3 to choose from. I think the difference is the size is 8 millimeters in diameter, 12 millimeters. I think you'd want to go with the smaller one because that has less surface area, so the heat will be more concentrated. On the other hand, it will also heat up faster, so, well, maybe you do want the 12. Let's check out this guy. Okay, so with our design, we'll be somewhere between 5 and 2.34 ohms with this guy. Not too bad. Let's check out the smaller one. Ooh. Wow, I didn't realize there was that much of a difference. Huh. Size does matter. With the smaller one, whoa, you get considerably less current, so I gotta say, I think this is the winner right here. The SL0812101. Fortunately, I don't have any, but I can certainly order some. Now, generally, you've seen me work on multiple projects at once. This is one of the reasons. So in order to place an order, I need to hit the minimum unless I want to pay an extra fee, or maybe they don't even let you order these days. I don't quite recall. I think the minimum is 20 bucks. So I like to plan future projects and order up parts. Or I order duplicates, like I'll probably get 10 of these and get the price break. These also cost less, 56 cents. If I get 10, it'll be a little over 5 bucks. Here's my test setup. I took the original thermistors out, which came out really easily. The wires were not wrapped around the lugs very well, which makes me wonder, are these possibly replacements? I'm not sure. Also notice one of them is curved a bit. Don't know if that's from heat over time or if that's just how it was made. At any rate, here are my new diodes. I used a pair, I should say, of 1N5408. These are rated for 3 amps. And here are the wires going down to the tube filaments. And there's my thermistor up in here. While I was down here, I did a little bit of cleaning up and some inspection, and unfortunately, one of the phenolic supports on the flyback has broken. And that's the one that goes to the business end. This is the high voltage winding on the flyback. And if I flex this, you'll see that that little wire coming out of that donut flexes. I don't think it's broken, but I don't like this. So what I'm going to try doing is reinforcing this. I'll use some epoxy and some bracing, try to straighten it out a bit, and then put some Corona dope or similar high voltage sealant on that. I'm used to this part of a TV looking a little worse for the wear. There's a lot going on in here between a lot of heat being generated by the horizontal output tube, and we got high voltage going through here, which can break down plastics over time. So briefly, There's an oscillator on the other side of this cage. It makes a sawtooth wave, goes into the grid of the horizontal output tube. That drives the primary on the flyback, which is a high ratio of secondary to primary windings. The high voltage is picked off of here, goes to the high voltage rectifier, anode. Cathode is down here. That's where you get your positive pulsing DC coming out. This guy is a ceramic high voltage capacitor to filter it to clean DC, commonly known as a doorknob capacitor. This is a resistor in series with the high voltage lead, which is going to that cap, which is currently disconnected from the CRT. They put a resistor there in case this falls off, shorts against the chassis. You don't take out any of these components here. Often these can be bad, so it's something to check. Not all TVs have them, but some do. Okay, so back to our test. How are we going to know if it's working? Problem is, if you use a typical multimeter and put it in AC mode, they are designed for pure sine waves. They take the sine wave, they rectify it to DC, do a little bit of mathematics in the circuitry, and give you a display value. We're not going to have a pure sine wave. We're going to have something like this. It's going to be a clipped sine wave. This happens to be a true RMS meter, so this can make sense of it. If you don't have one way, if you've got some experience, to just judge how brightly the tubes are glowing. I've also got a current meter built into the Variac I'm going to be using. I don't know how accurate it is, but I think it's in the ballpark, just from my experience with using it. So let's see what happens. Oh, one thing I want to mention. You may be thinking, hey, isn't there another way? Yes, there is. There usually is yet another way. Many ways to do modifications. So, all we've been talking about is the filament strings. Well, what about all this stuff on top? In fact, there is a 5 ohm, or was a 5 ohm resistor in series with the B plus supply. That is there to limit the surge current going to these rectifiers so they don't blow when you turn the set on. Well, how about we eliminate that, eliminate the other thermistor, and just stick one right on the AC input? You could. And a CL90, which is rated for about 2 amps, would be a pretty good application, because the set draws somewhere between 1 and 2 amps. Yeah, you could, and that would, I think, work fairly well. One of the reasons I don't want to is I don't want to modify this thing too extensively so that somebody would understand what was going on. So in order for me to do that, there'd be no thermistor here, and if I put these 2 diodes down below so they weren't affected by the heat of this tube, there would just be 2 wires coming down here. It'd just be a dead short between here and here, and somebody down the road might be servicing this and think, well, some moron worked on it. These were bad, and he just replaced them with a shorted wire, not knowing that there are 2 diodes and a thermistor hidden down below. So I kind of want to keep the 2 circuits separately, and I do intend to use some type of thermistor in this circuit as well. And also, these were seleniums. They were replaced with silicon, so it gives me a good opportunity to increase this value to get B+, so it's in the proper range. What value I will use, don't know yet. We'll determine that experimentally. All right. That was a whole heck of a lot of talking. Let's actually do something. So, sets off. I'm going to plug it in, turn this on. Set the output level. Oh, let's go to about 125. It will drop a bit when I turn the set on, assuming that we do have filament continuity. So here goes nothing. Oh, let's put this in current mode and see what happens when I turn it on. It should jump up a bit, because the filaments are cold. The thermistor will help, but it won't completely eliminate the surge. So it surged to a little over an amp, not settling down to just over, let's just call it half an amp. So I presume if that meter's showing half an amp, we must have tube glowing. Yes, we do. And that looks about right to me. If they were super bright or really dim, I would know something wasn't quite right. Now, how accurate is that? I don't know if that's true RMS or not. There is another way to do it. So this is a true RMS meter. This has a special chip in it that can do the mathematical calculations to figure out the true RMS value. But another way to do it, an old-timey way to do it, is to actually run your current through a heating element and see how hot it gets. And if you know the resistance of it and temperature, you can do some math, and you can figure out how much current is flowing with a complex waveform. Let's also check the output voltage, which has dropped a bit by now, probably. Let's get that up a bit. It's about 127. And now our current, it didn't go up too much. It's a little bit less than I'd like, assuming that that meter is accurate. And I'm going to gingerly see how warm that's getting. That's pretty toasty. That's probably close to the operating potential. Now, a final way I can do it is if I quickly turn this off and grab my meter and measure the resistance on that, I can see if it's pretty low and my math is right and the diodes are doing what they're supposed to be doing and all the tube filaments are doing what they're supposed to be doing. We can assume that the circuit's okay. So I'm going to try doing that right now. It occurred to me we can also look at this with some other test equipment. So I put an extender socket on the CRT. That goes between the CRT base and socket and has little tabs sticking out to correspond to the pins on it. So right now I've got my scope on the filament pins. And let's see what it looks like and what kind of measurements we can get. So there's that chopped sine wave I was talking about. So most meters and test equipment are not going to quite know what to make of that. Now I got it measuring volts RMS with AC coupling, and we've got about 4.8 volts. However, as memory serves, when I've tried doing this before, it's not that simple, because there's also going to be a DC component to it because it's getting rectified. So if we go into DC, now it's showing a volt RMS of 6.26, 6.29, 6.3. That makes more sense to me because the tube glow does look right. And from doing the math, with 130 volts or so going in like I've got now, it wasn't off by that much. So we got a little bit of noise and such going on. So, interesting. Well, let's see what a multimeter can tell us. I think it's going to have the same issue because it's got an AC mode and DC mode. You can't do both at the same time, I don't think. So let's go with the meter in AC mode. And we got about, it's tough to get on here, bear with me. About 4.7. What do we get if we go into DC mode? About 4, or minus 4, because the lead's reversed. Well, that's annoying. I remember going through this trouble before with you guys when I was trying to figure this out. So I think, unfortunately, with this meter, even though it's true RMS, can't really figure out the actual filament voltage with that. However, I do think the scope in DC mode is telling us what's really going on. I'm inclined to trust this And I think the solution can work, especially if I get that thermistor that has an even lower resistance. So one last thing I want to do is quickly turn this off and throw my meter into ohm mode, and let's measure the resistance on that thermistor when it's hot. About 10 ohms and climbing. So now, in normal operation, with these tubes running with plate voltage, they're going to be even warmer, which will help heat up that thermistor even more, which will drop it even more, so it'll have even less resistance. So I think this design will work. I think it's right at the edge of working, and it does require on your household line voltage being a little bit on the higher end, and the tubes are going to run slightly lean. But given all the advantages of it, very compact, very inexpensive, 2 diodes and a thermistor, it's probably less than $2. So I think we got ourselves a winner. Otherwise, AC motor run caps, they'd be about this big. But also I was doing a little bit of searching, and there are some Nichicon 10 microfarad caps. They're similar to this. Mauser sells them, or DigiKey sells them. They do have an AC rating. You can get 10 microfarad caps. I think they're 250 DC and 125 AC. And they are polyester film. However, when you look at the spec sheets, it says, even though we'll give you an AC rating, they're not meant for use across the AC line, and if you're going to be using them in any other AC applications, contact us. In other words, they don't give you any specs on how they perform in AC situation, other than telling you an AC voltage spec. So I cannot give those my seal of endorsement, but for short demonstration purposes, while you keep an eye on the set, they probably will work all right. I would not put them up in here because they're going to roast, but beneath the chassis for intermittent use, they're probably okay. I will put a link in the description to them, but again, I cannot guarantee that they will work properly. They are not rated for continuous AC operation, but they'll probably work, and they cost about $5 each. On a hunch, I logged on to my DigiKey account and checked my order history, and I found those caps. Those are indeed motor run capacitors, and that's small of a package. And here's the 8, and here is a 10. A little bit more expensive than using thermistors and diodes. It's over $5 for just one of these. But these are polypropylene. That's what you want to see in a motor run cap, not polyester film. AC power caps, application motor running. They don't give a current rating, but 300 milliamps is pretty low for a motor. So if this can handle a continuous motor operation, I think it's pretty safe to assume they can handle 300 milliamp load on some tube filaments. And maximum permissible temperature is 85°C, so I think these probably could live and function all right inside that high voltage box. Now for this project, I am going to stick with the thermistor and the diode, at least until the set is fully operational, and maybe I'll do another experiment with these caps since I've got them on hand. And it's certainly a viable alternative. Some of you may be thinking that this is one of the more boring videos I've done, and perhaps you're correct, but I thought it was a topic worthy of in-depth discussion. I hope you've gained some insight into a somewhat complicated topic, and we did some interesting experiments, and we know the tube filaments work. Hopefully in the next installment we will do a full power-up test with the B+, and maybe actually get some life out of this set.